I leave now the word, the scene to Dr. Veronesi, Giorgio Veronesi, who is the Vice Executive President of the European Federation of Chemical Engineering, and who will give a brief introduction to the webinar series. So please, Giorgio.
Okay, thank you, Bruno. Welcome to everybody. I'm Giorgio Veronesi. I'm Executive Vice President of the European Federation of Chemical Engineering, EFCE. I've been in the board of EFCE for 5 years and currently in my second term in this position, where I'm responsible for operational, economic, financial matters of the Federation. I'm a chemical engineer by training, graduated in Padova, Italy, and I've been spending the whole of my career in the engineering and construction business, involved in many projects, mainly abroad, with several assignments overseas. I'm very happy, therefore, to be involved in the introduction of this webinar on safety, as during my professional life, I had the opportunity to fully appreciate the importance of safety in the design, in construction, and operation. Let me say something about this webinar series. EFCE is organizing a series of free virtual spotlight talks on significant topics in chemical engineering. 11 of our technical groups, which are working parties and sections, are delivering short sessions of 3 or 4 talks by leading industrial and academic experts on chemical reaction engineering, education, energy, loss prevention and safety promotion, this working party, mechanics of particulate solids, mixing, multi-phase fluid flow, process intensification, quality by design, static electricity in industry, thermodynamics, and transport properties. Each session will focus on key subjects, and the series enables attendees to sample topics in areas that they find interesting, but may not otherwise have had the opportunity to attend before. In this way, we want to encourage cross-fertilization between specialist areas. Let me say something about the scientific collaboration. The EFCE promotes scientific collaboration and supports the work of chemical engineers and collaborating professionals in 30 European countries, representing more than 100,000 chemical engineers in Europe. EFCE working parties and sections cover all major specific aspects of chemical engineering and are in fact at the core of the organization, forming the scientific engine that drives many of EFCE activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. Before concluding, this was a very short introduction. I would like to thank all the people who work hard inside the working party and inside EFCE for this initiative to happen and to be successful. In particular, I would like to thank inside the EFCE, Martin Pou in Toulouse and Ines Wondorf in Frankfurt, who did most of the work for this webinar, from the conceptual phase to the setting up to all the practical aspects of this work. Having said that, I would like to thank you for your attention and wish all the speakers and the attendees a fruitful and successful webinar, and give back the word to Professor Bruno Fabiano of the University of Genova, Chair of the Working Party on Loss Prevention, to start the works. Thank you.
Thank you, Giorgio, for your kind words and your kind introduction. So my task in this opening speech is the simple presentation of the speakers. Nevertheless, allow me just a few words about the Loss Prevention Working Party for those who are not familiar with it. But first of all, let me express also my gratitude to EFCE for the webinar organization, and a personal thanks to Martin Pou and Ines Wondorf for their always effective and precious activity. Now I share my screen. I hope you see it. Well, the EFCE Working Party on Loss Prevention and Safety Promotion in the process industry, more shortly Working Party on Loss Prevention, began in 1971 as a group of very motivated professionals who decided at the symposium Major Loss Prevention in the Process Industries held in Newcastle upon Tyne that in view of the safety situation at that time, an international effort was necessary. And they found a roof under the European Federation of Chemical Engineering. The new approach to safety was called loss prevention and was originally directed to the prevention of the large-scale accidents and to set up measures to limit their possible consequence to an acceptable level. 50 years of loss prevention and safety promotion in the process industry are well outlined by the history of our symposia. Here we show the different hosting countries from the origin to nowadays. Next one will be in 2022 in Prague. And currently, the Loss Prevention Working Party consists of a mix of representatives of industry, university, and regulatory organizations, all members formally nominated by the National Chemical Engineering Organization. The symposium aims to be broad in its scope and to bring all process safety aspects together. I want to show this well-known slide, which shows the development of loss prevention aspects over a time span of nearly 50 years, promoted also by the Loss Prevention Working Party. This figure was originally conceived for safety management in 1995 at the symposium in Antwerp, and the author was Koos Visser of Shell. And since then, it was stepwise expanded by Hans Pasman, who is one of the keynote speaker of today. The Loss Prevention Working Party constantly aims at disseminating process safety, good practice, discover new techniques and approaches, gain experience and lessons from the past, incidents and near misses, allowing international networking among academics, industrial experts, consultants, and regulators. So, over the years, the safety community succeeded in getting better control of the risk of operation, and the attention shifted from explaining after the fact how the accident had occurred. We are designing and implementing protective measures towards prevention by inherent safety features and rethinking the processes. This webinar with leading chemical experts focuses on safety, on what we call safety 4.0. Why? We see the fast development of manufacturing, processing, and chain production, which is well known as safety 4.0, which includes the digital revolution, artificial intelligence, the Internet of Things, and the interaction with every smart devices, opening new possibilities of data gathering and processing, applying the tools of artificial intelligence and machine learning. Accordingly, new approaches are needed. And to re-engineering, let me say, process safety and the way technological risk should be managed towards the newly defined safety 4.0 introduced for the first time at the last EFCE Loss Prevention Symposium organized in Delft by Professor Genserik, Reniers. So, digitalization and data science form the gateway to make progress in risk assessment, enabling more precise and continuously updated predictions. So we can say here, we can see here how the classic areas of process safety can be integrated by novel approaches connected to digitalization, to machine learning, to resilience engineering. And from one side, emphasis is about identifying the benefits to the management of major hazards. From the other side, we must ensure that all the hazards of the technology are understood and correctly managed. Additional, some emerging issues like circular economy, sustainability, climate change, and consequent hazards from extreme weather events need to be fully integrated with the process safety paradigm. While resilience engineering, which is one of the topics of this webinar, and a system approach to process safety can represent promising challenges. The role of process engineering should include a critical and balanced application of new development in data science and digital technology with fundamentals, science, and engineering principles. On this basis, I mentioned next loss prevention working symposium, and which is the 17th of the series, and which will be organized in Prague. And some new topics will be introduced, also taking into account EFCE efforts to transmit the key messages relevant to energy transition, carbon-free and safe sustainable industry. Here you can see quite fastly the metric approach showing the new topics, the new challenges posed by the emerging problems, and the traditional topics of our symposium. And I showed just some expansion of the different topics: risk assessment, security and safety, lessons learned, case studies, human and organizational factors, leadership and risk communication. Here is the website of the event, which is the next event of the European Federation. But now, after this introduction, it's time to get this webinar off the ground, introducing the first speaker, who is actually a worldwide guru in process safety. I remind the audience that if there are some questions about the lecture, please write them by the electronic system, and we shall discuss them after the lecture. The first speaker is Professor Hans Pasman, who is a research professor at Mary Kay O'Connor Process Safety Center at Texas A&M University and emeritus professor in chemical risk management of the Delft University of Technology. He investigated several process industry accidents, and his research included the reactive materials, dust and energetic materials explosion, risk analysis. Since 1972, he is member of the Working Party on Loss Prevention and Safety Promotion in the process industry, and is currently always with us. So please, Hans, the share is yours.
Right, I shall share my screen. Okay. And now I have all you in my, okay, so, right. I'll talk about process and plant resilience and why it is necessary. Well, the answer in a few words is already down there. To be safe requires assessment of risk, and assessment of risk will be incomplete. Resilience can close the gap. Okay, I'll explain. The overview of the lecture is as follows. Plant of the future requirements. What is resilience? Risk assessment methodology, just a quickie. Limitations, uncertainties, and improvements. System approach. Industrial application and business continuity. Conclusions on plant facility site resilience. And that is the whole story. Now, we start with plant of the future requirements, and maybe you come from all kinds of, say, specialisms or very general. So you have your own view on requirements, I'm sure, but just in a few dots, and high product and energy efficiency, and flexible to change, because the dynamics in the world have greatly increased. Markets, prices, requirements, everything changes. So you need to have flexible processes. Well, in the long term, Industry 5, now we have Industry 4, but in the long term, Industry 5 is perfect human-machine interaction. Then sustainable process with respect to materials and energy carriers. Safe to work in and acceptable with respect to risk in the vicinity and in the environment. Resilient, to ward off, protect against, and quickly recover from unexpected threat damage. And all enabled by abundant data and analytics. Right. Well, here is just a schematic of resilience of a plant or a process. Well, two cases. The normal case is case one, when it is hit by a disaster. Of course, there is a certain extent of damage and destruction that can go very quickly or not that fast. Then you have a time to prepare what shall be done and to plan your recovery measures, and finally you may come to your original performance. Case two, same thing, but they have resilience measures applied. So they are much less damage and much earlier on the performance again, and maybe even a better performance than before. Now, what disaster types can be there? Well, the natural ones, think of high winds, tornadoes, flooding, earthquake, that kind of thing. Technological, I mean, you can have a release of flammables and an explosion, maybe a very heavy explosion, with lots of damage. Environmental is more in, let's say, toxicity aspects, and human-made. Human-made is, of course, cyber attacks, terrorist attacks, sabotage, and there will be also some lecture on that today. Now, the definition of resilience, there are many in the literature, but one is a very authoritative one, and that is by the US National Academies, and that is in 2011, 2012. It is the ability to anticipate, prepare for, and adapt to changing conditions, and withstand, respond to, and recover rapidly from disruptions. In fact, what you have seen in the schematic. There is also a kind of mathematical notation by Steen and Aven from Norway in 2011, contrasting it against the risk concept. Now, the risk concept is a function of the type of attack, barriers, consequences, probabilities, uncertainties, and background knowledge. A subset of that vulnerability looks at the, let's say, targets that are attacked. So it is the barriers, consequences, probabilities, uncertainties, and knowledge given an attack. And the complement of that is robustness. Resilience is, well, broader in the sense that it is the same function of the barriers, etc., but given any attack, including new types. Because we are very bad as humanity to look into the future. Well, the concept here is more comprehensive than the one by Holnagel, Woods, and Leveson that was launched in 2005, 2006 as resilience engineering. The word engineering here is, in my view, a little bit confusing because it is not looking at the hardware of a plant, just the people. And of course, you can strengthen the resilience of the people, and they call that engineering. But we go here a step further. Well, I worked with 2 PhD students, and another one is coming already for almost 10 years on this aspect of resilience. And we developed this kind of quickie, so to speak, that is inspired also by the work of Trevor Kletz on inherent safety. Because everything starts with the design of your equipment, and inherently safer is certainly part of it, but it should go a step further, namely error tolerant design. So it means that the equipment is, or the design of the equipment is taking account of a human being and what a human being has of capacity to decide the time that he needs to do that, etc. So it is human friendly. Then next is that if the operation is going, you should detect early warning signals. And that is to be warned ahead of time and to avert any disturbance that otherwise may come. Well, that is not an easy thing to do. I can give you several examples of, well, in fact, Mr. Trump and the COVID in the US, the CEO of Boeing, there were warnings in the organizations, but they did not reach the top. Or if they reached the top did not take action. So that is the next thing, plasticity of thinking. That is resistive flexibility. You should be, as a management, open to things that suddenly can come up and take the right decisions, but you need not to jump to conclusions. So it is a kind of difficult thing to do. And then if you take that decision as a management, you have to muster your crew, your people, to prepare for emergency response and for recoverability. Okay, so again, design should be human-friendly, flexible, and minimize hazard. Threat signals should be identified and communicated upwards. Management should act and measures taken or improvised, and recovery measures should be prepared in advance with reserves. For the best result, it assumes that you did your risk management right. Risks are many. Okay, a very quick overview about risk assessment for those that are not confident with it. If you start, please first establish the context with the objectives, your stakeholders, criteria, and the key elements. That is very often not done. Then identify the risk. And I highlighted that because that is most important, and it is the weakest part of the whole risk assessment. What can happen and how can it happen? Then analyze the risks, okay? Consequences, likelihoods, and you get a certain level of the various risks. You evaluate them, rank them, and then treat them in the sense that you try to reduce by selecting measures to minimize them, or at least make them acceptable. Right, so the tools that are known in hazard identification, identify the risks, are HAZOP and FMEA, so that's hazard and operability studies and failure mode and effect analysis. Very old tools, already from the 60s and 70s. Are they reliable? Well, only to a certain extent. It depends very much on the quality of the team doing it. But even the best team can overlook certain hazards. Evidence of this is amply available. There are quite some publications with experiences what has been overlooked. Are there improvements possible? Certainly. Big data will give relief, but we do not know yet to what extent. So resilience building is a must, because that should protect. Right. Possible factors that make the hazard identification so uncertain is external threats to the plant are usually not taken into account, although there is some trend there for improvement. And then there are lots of internally contributing factors. Human failure is in many forms. And for a long time, there was no human failure really accounted for in risk assessment, or very implicitly, but okay. There are always hidden things, and also in design errors, functional and material, organizational factors, miscommunication, bureaucracy, all kinds of delays, hidden correlations and dependencies between components. Only the last 5 or 10 years, it becomes possible to deal with dependencies between components, determining another failure. In risk analysis, there is lack of context definition and bad definition of the system. Wrong interactions of correctly working elements that lead to non-linearity and dysfunctional of the system. So you have everything looks all right, but still there goes something wrong. That you can see from the system approach, the socio-technical system that was introduced to this field of process safety for the first time by Jens Rasmussen in '96, and Nancy Leveson in the States at MIT has very much expanded that. She started with a stamp, an accident investigation investigation. And well, the system is given here, and starting at the top, regulators, company management, operations management, and the operating process with the human controller and the hardware. So you see a layered and hierarchical system with communication or orders coming down and feedback with information going up. And Nancy Leveson has added to that pillar on the development stage, because there is already a lot of things happening, constraints that are maybe just exposed themselves in the operation stage. Maintenance is in between, because maintenance for a large part is determined by the development, but also by the operation. So yeah, system is more than the sum of parts. A complex system is the hierarchy of organizational levels, as I showed you, connected by information links. And complexity is not a system property. A lot of people always say the system is complex, but what they mean is our brain cannot see right away what is happening all in that system. So it is a limitation of the mind. And safety is emergent. That is, it comes out. It is not, you cannot put your finger on it. It is emergent. Okay. Now, with respect to resilience, from a company point of view, it all starts, of course, with leadership and culture, because the leader determines the culture. His staff engagement, decision-making, that requires situation awareness, and of course also for measures, innovation and creativity. Well, the organization has to be change ready. It means that you need testing plans, stress tests, really, proactive posture, planning strategies, unity of purpose, and then the network may help very much in getting information and early warning. So that requires effective partnerships, internal resources, leveraging knowledge, take the right conclusion, so to speak, and very important also, breaking silos in your own organization. That the silos, what I mean is just the walls between organizational groups. So the precondition of all is strong leadership and effective management. And the result is business continuity. For emergency response point of view, you see, you can put up the same kind of cycle, because it starts all with scenario analysis, so that the people that have to do it have a certain scenario in mind and are not too much surprised when they have to really act. So prepare and train, that is next point. Analyze weak signals, anticipate. And then if disaster or crisis hits, you have to respond. That also includes self-rescue and firefighting and medical first aid. And of course, then you get to assess the damage, to reconstruct, restore, and while doing that, think about reducing the risk by inherent safer protection and mitigation measures. Again, precondition, strong leadership, effective management. Right. Now, the resilience matrix. Prerna Jain and in our second PhD student, now working for Exxon, by the way, we developed a number of metrics. Well, the metrics on business continuity are just literature ones, because there is a lot of resilience on business continuity, and that is business resumption response time, quite obvious, recovery time, recovery point objective, that is the maximum amount of data loss that should be occurring during the disaster, return time objectives, and maximum tolerable period of disruption, more or less the same. Now, the resilience metrics for the process of the plant, that are many, based on the socio-technical system. So it is part people and in part the hardware. And that are things that you can measure. So you can take periodically an observation of their numerals and take that and look at that for a longer time. So it is kind of leading indicators to a certain extent, but more directed towards resilience. Right. Now I come to the process resilience analysis framework. And that is that you of course look first at the whole system architecture of plant, people, and procedures. Uncertainties, continuous and discrete. So, and then, well, you have to do a predict for survivability and recoverability. There are inputs, and there are, of course, the business impact outputs. But this is the most important part, because here you do a lot of analysis, risk assessment, dynamics, simulation, and I'll come to that next page. First, we need data. Okay, that is the plant, people, and procedures. Then, of course, as far as possible, the hazard identification. Process historical operational data. The resilience metrics that you have monitored. The safety management system metrics. That is the lagging and leading ones. And then the maintenance, so what is coming out of the maintenance management system. Various methods of statistical data analysis and natural language processing are required to sift out early warning signals, especially the process upset ones. And that is today with digital twin models, where you can also study the dynamics. And with respect to people, congruence analysis, where you can see or can analyze the dependencies of tasks of one human with respect to the other. And of course also the possible failures. Then machine learning and artificial intelligence provide the many data reading interpretation possibilities to obtain prediction of threats and risks, including uncertainty analysis. The result is, well, pattern recognition, random forest decision tree, and hierarchical patient analysis. A lot of details. Okay, then a definition of measures to survive and recover and strengthen resilience, and what is in the selection the best cost benefit. What is at risk? And measures one can take. At risk is the human base, your people, the market share, facilities and equipment, not to forget your reputation. We know it all. Okay? Well, I will not give any examples here, but there are quite a few to mention. Financial resources. Somehow you need reserves. Intelligence is very important. That is, of course, in connection with the early warning. Cybersecurity, effective emergency response in the plant and in the region. Because very much as you have a big disaster, you need response teams from various parts of the country or even from neighboring cities or whatever. And that has to be trained. Building contingencies reserves. Okay, there are ways to optimize cost of risk reduction versus the reduction of the risk. Pareto kind of curve with the risk acceptance level here, and well, the best point there. And of course, you can do that in an overall thing. So with all the data that you have, your analysis, your risk analysis, your resilience analysis, you can also look at the economic optimization and profitability. For decision making, you must know your residual risk. And by the way, we are a risk assessment, we are very often, well, if a risk is acceptable, that maybe even a large consequence, but a very low frequency, we are inclined not to look at it anymore, but it can still happen, and that we should not forget. So my conclusions are, resilience is an umbrella for bad weather. It is an insurance to sustain unknown and unexpected threat. Investments in efforts to achieve it will translate in sustained business. It requires an attitude and a way of thinking, up and beyond good process safety. It needs to be applied over the whole chain of design to operation, and it starts through risk assessments based on the socio-technical system approach. Big data is around the corner. It will help in many ways to obtain information and hence knowledge of sneaky downward trends in performance and complex interactions. Process models, indicator data, and machine learning will help to obtain early warning signals, enabling improved maintenance, reliability, safety, product quality, and process dynamic adaptation. These are the references. By the way, this article that is in here in sustainability of this year is a kind of summary article of the work of the last 10 years so far. But you find the others here. So thank you very much. And if there are any questions, I will be happy to try to answer.
Thank you very much, Hans, for your illuminating and new message. Let me say, I'm sure that all the attendants get your message loud and clear regarding the actual challenges connected to resilience engineering and the system approach. I remember a long journey was made since you presented for the first time resilience in our community at the Florence symposium. So very nice. So I have some questions. And what are the most useful metrics for evaluating and ranking risks in order to support prioritized implementation of control actions?
Control actions.
Yeah.
Yeah. Yeah. Okay. Well, you have to look at, of course, what is already there in safety management indicators. But to translate that into control actions, you have to go into the system, socio-technical system, and the methods that Nancy Leveson developed, okay? And well, looking backwards, she developed STAMP into CAST, that is for accident investigation. But for here, you have to look into the future, and then you need system theoretic process analysis. Now, that is in principle a very good approach. However, so far it has been not used very often because it is very, very labor intensive. So yeah, there will be very shortly a publication by Paul Babert on whether HAZOP should be changed for STPA. But so to define all your controls and control actions to monitor is a huge job. I can see it that it will happen in longer term and with a lot of computing. That's the only way out. Of course, our minds are much too limited to contain that.
Another one which opens a wide discussion and in which you are very, very expert, and an attendee asks if whether are there better alternatives to current methods, HAZOP, failure mode and effect analysis, checklist, what if analysis for hazard identification, and it's open the sea, yeah. Let me say.
Well, of course, I can say that there are efforts underway, and again, also this year, recently another paper. Well, HAZOP can be automated for a large part, not for 100%, of course, but using ontology, CAPE ontology, so you have computer descriptions of your equipment, and the system of HAZOP connected to that, it is possible to do a better job than just a human team can do. Okay, so it is you will not be able to do it without humans, not at all. No, you need the experience, you need the people that can look through things, but computers can help very much. There is, of course, one guy that is Robert Taylor. Robert Taylor was a long time also in the symposia, the loss prevention symposia. He has an enormous experience in HAZOP, and well, he was able to look back what happened to the plants that he HAZOPed in a number of years, in 30, at least 30 years, if not more. Right? So he, and at the same time, he developed for himself, but the software for automation to help him in his HAZOP effort. And although also that is, he published recently, 2018, or in PSEP, I think it was. So, but it is not software that is let's say, made accessible to anybody. I mean, it is not user-friendly, so to speak, I think. That is the problem. So, yes, it is not without any hope. No, there is certainly perspective. But we have to be patient and we have to work on it.
Thank you, Hans. We have several other answers, but
yeah,
to be replied, but time is running, so you can contact directly, I believe, Hans. I will leave the email at the end of the webinar. So we can move to next speaker. If I can share, can you?
Yeah, I stop sharing.
Yeah. Okay. Okay. Next speaker is Professor Valerio Cozzani, who is a chemical engineering professor at the University of Bologna in Italy, where he leads the Laboratory of Industrial Safety and Environmental Sustainability. He is a very well-known expert within the safety community worldwide. He has several years of experience in research on process safety, sustainable design and technology, and innovation in chemical processes. He chairs the ESRA Technical Committee on Chemical and Process Industry, and he is member of the European Federation of Chemical Engineering Working Party on loss prevention in the process industries. The topic of his speech is Natech scenarios due to the interaction of chemical and natural hazards, a new challenge for process safety. So please, Valerio, the floor is yours.
Thank you, Bruno, for your introduction. As soon as possible, I'll share the screen with all of you. Okay, so should be shared. If not, please let me know. Perfect. Okay, so Natech scenarios. are a quite specific issue concerning and affecting the chemical industry. They are actually composite scenarios in which natural events are expected to impact on industrial facilities to cause loss of control or structural damage resulting in the release of hazardous substances, generating a technological accident. So actually what is specific of these Natech events is that they are cascading events in which actually a first type of event, a natural event, generates a technological scenario, and the consequences of both events may impact on the assets, on the workers, on the nearby population, and on the environment. So it's mostly this cascading feature that is the more alarming one of this peculiar type of accident. Let's see an example. It's a very well-known accident that took place in 2017 in Texas after the impact of Hurricane Harvey on the south coast of the Gulf of Mexico. The facility that was involved was a site of Arkema, an international chemical company that produces peroxides as initiators for polymeric reactions. Actually, on the 26th of August, the Arkema site in Crosby, Texas, was shut down due to the approach of the hurricane. Then what happens a few days after, you see on August 28th, was that a flood reached the plant and caused a power outage. At the same time, backup generators were submerged, so there was no backup power supply. And this resulted in the stop of the refrigeration units of the peroxides that could not be refrigerated and could not be driven away due to the flood of the main roads connecting the site to the escape routes in the safe direction. So there was no way to avoid the peroxide to gradually heat up to ambient temperature. And this happened 3 days later on the August 31st, when suddenly the peroxide began to decompose and caused repeated explosions. Peroxides and terbutyl hydroperoxide was involved in the accident, have a low flash point and violent and experience violent self-decomposition. And this was the result of the event, huge explosions and release of toxic fumes that forced to an evacuation of population and resident population in a radius of about 1.5 miles around the site. Now, what caused the main hazard to the workers and the population? By the way, policemen that were governing the evacuation were badly affected by the toxic fume. So, what caused the harm was the technological scenario, was the composition of peroxides and the following explosion. But what really started the chain of events was the flood. Even if the flood was slow and gradually affected the site so that no worker was affected by the starting event. But now, this is a kind of paradox. That means, how can this be a new challenge for process safety, since it's a kind of combination of two well-known hazards? Because flood was an initiating event, but if you allow me, actually flood is a very well-known hazard to humans, And if you see this nice fresco, which I invite you to visit in Italy, it's in the Sistine Chapel from Michelangelo, and it represents the Great Flood. Every culture has this tradition of floods affecting humanity and threatening life. At the same time, the hazard due to peroxides, maybe more recently, but still it's well known and widely investigated. Here I collected a paper on Nature dated back to 1938, where the hazard of peroxide is cited and analyzed here in Europe. So these are old, and both the technological accident that took place in the Arkema site and the natural event that affected the site are well-known hazards. But still, how can it be that these two well-known hazards still resulted in an accident on the one hand, and on the other are a kind of new challenge for process safety and for the chemical industry in general? The point is, on the one hand, that what took place in the Arkema site is a combination of the two events, more precisely a cascading event. That means first there was a flood, and then due to a number of unforeseen consequences of the flood, a technological accident spread out. So actually, what happened there was that a facility that we can consider safe from the point of view of conventional process failures was actually found unsafe when external hazard causes played a role as the natural event. And this is a first point. A second point is that Natech events are what we call high impact, low probability events. That means they're events that have a time of return or a frequency that, luckily enough, is low, so that it falls outside the everyday experience of operators and of facility managers. A third point is the complexity. The chain of event of Natech accidents is usually quite complex, and it's not easy to understand what actually may happen and how actually the accident may evolve. And this was the case of Arkema, where four safety barriers, four layers of safety barriers that were considered to be independent and actually were independent in normal conditions, revealed to have a common cause of failure. And finally, last point that is that the time of return of some climate-related extreme meteorological events is progressively reducing, possibly due to climate change. And this, in perspective, requires adaptation strategies to be implemented by industry. All this makes the prevention and mitigation of Natechs a complex issue and somehow a new challenge for process safety, even if this type of events derive from widely known hazards that affected humanity and more specifically the process industry since their beginning. Concerning complexity, it is important to understand which are the features of a Natech scenario. In particular, in a Natech scenario, a natural event is the starting point of the sequence of events leading to the final consequences. This means that differently from a conventional accident that we deal with in the process safety domain, we are actually dealing with an event that is impacting on a wide area. and we might have that more than one unit or that several process units, but also utilities, are affected at once by the natural event impacting on the site. A second point is that usually the natural event causes a failure of one or more structural element of the facility, storage vessel or any other type of process equipment. And this results in the release of a dangerous substance that evolves with specific features due to the conditions that occur during the Natech event. And finally, there is the possibility that this technological event further escalates, also because the safety barriers that are in place to mitigate the consequences of accidents, as we will see later in this talk, are actually likely to be affected by the specific features of the natural event and may have a lower performance than expected during Natech events. A further point that is important to remark concerns the feature that we have already mentioned of Natech as having a high impact and a low probability. That means that these events are falling outside the experience of risk managers and are deemed not credible. This hinders appropriate resources to be dedicated to their assessment. What happens with Natech? What you see here is an ideal plot in which on the y-axis you have the frequency, on the x-axis you have magnitude. On such a plot, you can track an isorisk curve where you keep constant the product of frequency by magnitude. Usually, everyday's experience deals with conventional risks. Conventional risks are not specific of a particular activity or a particular site, are accidents that are that may affect any type of site. Just to give some examples, workers entering equipment where there are hazardous substances that have not been properly purged, or accidents due to the release of loads from a crane, and so on. All this is in our everyday experience, unfortunately, and these types of accidents are those that are effectively tackled by conventional risk management systems. While when you deal with Natech events, you're in the region of the curve where the frequency is low and the magnitude is high. And it's the region where the accidents are in the domain of experience of academic conferences, the one of today, or of very experienced practitioners that are not frequently in charge of the conventional risk assessment procedures. And this makes it more difficult for the identification. So that's why in the case of Natech events, the challenge of an appropriate identification is something that is in part still to be explored. We can consider that all process facilities in the chemical industry have on the site an appropriate risk assessment and risk management system that is designed to avoid the possibility of accidents by a number of barriers. Still, this type of risk assessment and management systems are designed to operate contrasting accident causes in ordinary conditions. That means it is seldom done to test these barriers and these systems immediately after an earthquake or during a flood. And this means that the risk management system may be affected during Natech accidents by the very particular and very specific conditions that take place during the accident. This is the reason why, even if risk assessment and risk management are standard procedures, their extension to tackle with Natech events is quite recent. That means actually that most of the work done in the quantitative assessment of Natech started in the last decade and produced results. Well, the first published paper is in 2007, and this is due to the fact that before it was not recognized that after an appropriate design of the facility to, let's say, to be safe with respect to earthquakes and floods and so on, still there was a residual risk that needed to be managed to avoid technological accidents to be caused by the Natech events. As I told you, in the last decade, there has been a lot of work on the topic that allowed setting up a framework for the quantification of the risk due to Natech events that is based on a few specific tools that integrate ordinary quantitative risk assessment procedures, either conventional ones or new approaches as those based on Bayesian networks. These points concern the availability of a simplified description of the expected time of return and intensity of natural events that may affect a site, the availability of models for the vulnerability of equipment, the availability of event trees that capture the specific evolution of Natech scenarios concerning both the issue of safety barriers that are usually present to mitigate the accident and the specific issues caused by the, for example, by the reactivity of the substances that are released with the flood water. And finally, there are issues concerning the need of taking into account the possibility that you may have more than one accident at the time. What I mean is that when an earthquake or a flood may affect a facility, it is perfectly possible that you have more than one equipment failing, so more than one release of a hazardous substance at the time. This framework simply didn't exist 10 years ago, and since then there has been a lot of multidisciplinary work that was carried out. For example, in developing what can be called the key enabling models to afford the assessment of Natech, that are models trying to capture the potential causes of releases of hazardous substances from process equipment in the case of natural events. And here you have an example of a schematization of the action of a flood on a storage tank. This type of models can be developed with a different level of detail. That means here you see an example of a very simple empirical model for an atmospheric tank, or you can have a detailed finite element model for the same tank. But obviously, when you aim at carrying out a quantitative assessment on an extended facility, you need, at least in a preliminary step, you need this type of simplified models to carry out a screening in order to identify the critical items that are more keen to fail in the case of the action of a natural event. This type of models are now viable for floods, for earthquakes, for lightning, for tsunamis. That there has been a lot of work from the academic community in order to understand this point. A further point that was made possible by the early framework for the quantitative assessment that was developed was to understand how the risk due to Natech events may change the overall risk figures in a facility. In this plot, you see here on the left, on the y-axis, the cumulated effect and the cumulated frequency of all the accidents that are possible on the site that may result in a given number of fatalities, n here. On the x-axis is the given number of fatalities. This means that a step here, let's say this point here, gives here on the x-axis a reference number of fatalities. And when you read on the y-axis, this is the total frequency of all the possible accidents that may result in that number of expected fatalities. This is the so-called FN curve. And this is how it is expected to change in the case of Natech events. It is expected to increase in frequency, and the reason is that the time of return of severe natural events is usually high in some areas of the world. A severe earthquake in Italy may have a time of return of about 1,000 years. That is high in the framework of earthquake engineering, but it's very low if we compare it with the frequency we would allow for a severe accident in a process facility. On the other hand, the problem of a natural event that may impact on an extended area means that due to the cascading features of these accidents, due to the fact that more than one equipment item may be impacted, and to the fact that we may have multiple scenarios, the expected severity of the accident represented by the expected number of fatalities in a virtual scale may increase. And so this means that we may have an important modification, an important increase in the risk profile of a site if we consider this type of events. And this is even exacerbated when you consider that the increase will affect accidents, the possibility of accidents with a high number of fatalities due to the wider impact area of technological events. This means that if you go to the expectation value and to the perception of risk, the perception of accidents with a high number of expected fatalities is usually higher. That means that you are increasing the risk in a region where actually regulatory authorities would rather ask you to reduce or even eliminate the possibility of such scenarios. It is important thus to consider if safety barriers can have a role in limiting the risk due to Natech events. Safety barriers are used to control this type of risk in chemical, to control technological risk in process facilities. However, in the Arkema accident, 4 barriers failed. So the ordinary power supply for refrigeration, the subsidiary generators, the possibility to move away the peroxides, the refrigerated containers, all these barriers were not independent and all were found to have a common failure mode in the case of a flood. Unfortunately, this feature of the Arkema accident was found from not to be the only one. A number of accidents were recorded where the failure of safety barriers due to the natural event actually had a role in exacerbating the consequences of the Natech events. So the failure or the performance modification of safety barriers is expected to play a negative role in the case of Natech events. A framework, the original framework for Natech can be modified to include the effect of barriers, and this is what was done in a recent work, where a performance modification factor was investigated by a survey involving experts. This expert survey transformed verbal answers from the experts on a probability scale that was used to define a barrier performance modification factor that was used in a specific approach to modify the probability of failure on demand and the effectiveness of the probability of failure on demand of active barriers and the effectiveness of the action of passive barriers. Here you can see how this performance modification factor was estimated from the expert survey that was carried out, and you see that a strong reduction in the effectiveness of some barriers, F stands for flood and E, F stands for flood and E stands for earthquake. You can see that values as low as 0.15 can be obtained from this type of assessment. So some barriers are actually not effective or should not be considered as present during Natech events. When including this in quantitative assessment by an appropriate event tree analysis, it is possible to calculate the modified risk figures. And here you have the final results. This is the standard case where barriers are considered in the analysis, and this is the probability of unmitigated scenarios, so scenarios where there is no mitigation from safety barriers. When considering earthquakes or floods, you see that the probability of unmitigated scenarios may increase up of about 3 orders of magnitude because the barriers can be hindered by the event. So with this recent result, I can come to some conclusions that are even if they are a combination of well-known hazards, Natech events are high-impact, low-probability events that need to be considered in safety assessment and in process safety. And what is more important is that differently from conventional accidents, the safety barrier performance may become critical and may be much lower than expected due to the the simultaneous impact of the natural event. The resilience of safety barriers and the independence of the protection layers thus is an additional issue that should be considered when analyzing Natech events. That's all. I only have to give some acknowledgements to all my co-workers, and in particular to Alessio Misuri, a brilliant PhD student that helped me to obtain some of the results I have presented to you. So thank you for your attention.
Thank you very much, Valerio, for your clear and eye-catching and eye-illuminating presentation. We have some questions, as it raised in interest among the participants. An anonymous asks if the evaluation of domino effects, which is usually treated into safety regulation, but is it possible that in the future Natech events must be part of a site analysis?
This is not the future, at least not in Europe and not in Italy. Natech events are actually part of the events that should be considered when issuing the safety report for the so-called Seveso sites. That means the chemical sites that fall under the obligation of the Seveso III directive. With the implementation of the Seveso III directive in 2012 in Europe, there was the additional requirement to consider also accident scenarios triggered by earthquakes and floods. In the update of safety reports in Italy, the regulatory authorities are asking to companies to comply with this requirement. And actually, I was asked by several important chemical companies to provide some criteria and framework for this assessment. And obviously, I'm not the only one asked for this. So this is not the future, at least in Europe, or at least in those countries of Europe as Italy, which are particularly exposed to natural hazards. Obviously, around the world, the perception can be different. There might be that more time will be needed for these regulations to spread out all around the world. But I think that since the climate is changing and this type of accident is affecting badly also the assets, industry will have a strong pressure to implement appropriate protections and update the assessment of this type of events in the framework of adaptation to climate change. So I'm confident that there is a mutual interest, both from the side of companies and from the side of regulatory authorities, to increase the protection of chemical sites from this type of events.
Thank you. Then Jochen Batz argued that you take Natech events scenarios into consideration only by emergency management and response, but he wrote this comment before the last part on barrier, I believe.
Okay. These are all parts that should be taken into account. Emergency management and emergency response is actually very important and should be different in the case of Natech accidents. But obviously there are several parts that you should consider. Safety barriers, but also the structural design of your facility. At least in Italy, our colleagues in structural engineering are working hard to design industrial structures and storage tanks and process facilities that are safe in the case of seismic actions. And the same, I mean, there are some simple protections you can adopt to decrease the risk of failure in the case of flood. Obviously, this is easier for new facilities. In the case of existing facilities, the mitigation of Natech risk is more demanding, but still there are strategies at several levels for this, but this would require another talk. So next time I will be happy to present this.
Okay, thank you, Valerio, also for the nice discussion. And now we can move to the next speaker.
Thank you.
The next speaker is Dr. Ming Yang. He is a young researcher, and you should be not surprised of because we choose to leave the floor also to a young scientist, as young people is the future of process safety, and the EFCE is promoting Excellence Award, and the next Loss Prevention Symposium in Prague, we shall award the 5th Excellence Award in Process Safety. So Dr. Ming is Assistant Professor of Safety and Security Science Section in TU Delft. He holds a PhD in Oil and Gas Engineering at the Memorial University in Canada, and he holds a Bachelor of Engineering in Chemical and Materials Engineering from the University of Shanghai in China. His areas of expertise include process safety, asset integrity management, probabilistic risk assessment, risk-based approach, management of offshore operation, and marine transportation systems. So, Dr. Yang, you are allowed a 20 minutes presentation, as we are a little late. So the floor is yours, please.
Thank you very much, Bruno, for the very nice introduction. So let me share my screen first.
Yes.
Okay. So I guess everyone can see my screen. So if not, just let me know. So good afternoon, everyone. So my name is Ming Yang. So I recently joined TU Delft as the assistant professor. So so today I'm going to talk about the asset integrity management in the process industry, and probably I can introduce you some of the new concepts of the new development in this area. So we all know that ensuring the integrity of a process system is actually very important to its safe operation. And a very good integrity management plan will also ensure that we have people, a system, process, and resources which is required to maintain a system integrity also in place and in use. And they will also perform when they are required over the whole life cycle of the process system. So in the next 20 or 25 minutes, I will briefly introduce first the history of the asset integrity management, and I will also talk a little bit about how we can handle the risk in the asset integrity management and what we should do, and some of the new concepts, the new developments, for example, use of the digital twin, use of the machine learning approaches, and I will try to link the machine learning approaches to the information series. And afterward, I will give you a few of the brief takeaways through the presentation. So a little bit more about the history of the asset integrity management. So we know that in the 40s, so the earliest known approach in the maintenance or the inspection was the breakdown maintenance. So we will say that up to the 40s, the maintenance cost was considered as an inevitable cost, and the only maintenance carried out was, we will say, the breakdown maintenance. This was feasible, and at the time that there will be limited number of components in the system, which I mean that the system is not that complex. So then later we will see a rapid growth of the complex systems brought by the Industrial Revolution. So then the breakdown maintenance may not be that cost effective. So in the 60s, I would say that the detection of the degradation of a specific component in the system was used to minimize the breakdown. So this is what we call the preventive maintenance. So in these maintenance strategy, the degrading components were replaced either under a age replacement policy or probably a block replacement policy. So basically the device is replaced upon failure or at a certain period of time or interval. So then in the 70s, So we now move to a era of reliability-based maintenance. We say that a more integrated approach to maintenance involving a very close linkage to the reliability and maintainability of the system was very well recognized. So the idea on the maintenance modeling and the condition modeling based maintenance, I would say, were also proposed or developed during this period of time. So then you will see also a very rapid growth of development of mathematical models and also the computational capacity in the early, I would say, 90s. So some of the preventive maintenance strategies gained the dominance in the asset integrity management strategies. So then also at that stage, the use of the non-destructive tests, the NDTs, started playing a very important role in the degradation, detection, evaluation, and so on and so forth. So we also see a lot of applications of the mathematical models using the NDT data that were developed to use the degradation process information in order to optimize the maintenance planning. So now, if we move to the 2000s, so the new approaches that evolved into I would say, include operational research and also the risk-based maintenance models. So the modeling of the entire components in a very complex or very large process facility is actually not feasible. So what we do is that we will identify the high-risk components and rank them and then analyze them. So the risk-based design models were just focused on these high-risk components. So that then people started working on the predictive maintenance of these components. So then we will say that it is always more attractive to use the predictive maintenance than the preventive maintenance, because it can predict and prevent failures and also some of the unnecessary shutdowns. Moving to the 2020s, you will see some of the new development of the so-called real-time condition monitoring-based maintenance planning. So it is a sensor-based monitoring technique which aims to enhance the productivity of the system, operation, asset integrity, and also the process safety. So these data generated through the condition monitoring process can be utilized, I would say, to assess the fitness for service, and also can be used to optimize the risk-based inspection frequencies, so the maintenance resources, as well as the extension of the lifetime of the process system. So that is actually a brief history of the asset integrity management. So when we move to the new era of the conditional-based asset integrity management, I would say that the risk must be or should be treated in a dynamic manner. So because we actually are dealing with this stage, the operational data. So considering the material degradations, the change in the external environment, the human operators' attitude or whatever, so this must be treated, the risk must be treated as the time function. So how we can dynamically assess the risk. So this is not a new concept. It was a concept proposed, I think, back in 10 years ago. So basically, we started a selection of the unit or asset that we want to study first, or to do the risk assessment first. So once the unit or the asset is selected, then we will find the most credible failure scenarios or the accident scenarios. So based on the given accident scenarios, we do a consequence assessment according to different types of or categories of the losses. So, and then ideally these losses should also be assessed in a dynamic manner or dynamically. So based on the design stage data, then we can also assess the prior probability of failures of the asset or the process unit. And then based on the real-time process data, so the real-time condition monitoring data related to that asset or the system, so we can keep updating the prior probability of failures and try to get the posterior probability of failures. So eventually, so we can assess the risk in a dynamic manner. So this is how, I guess, how we should handle the risk in the nowadays the asset integrity management. So, so this is a quite generic model that we developed before for the real-time asset integrity management using the condition monitor data. So you will see that you were studying the process from the identification of monitoring parameters. So what are the different process parameters are you going to monitor? And what are the different asset integrity related parameters so you would like to choose to monitor? So the data pertaining to these progressive defects or the process deviations are also collected using probably multiple sensors, such as the corrosion probes, the inline inspection, the PICs, and also the fiber optic cable sensors. So then you will also try to collect the defect data, and these defect data may include the corrosion, cracking, dents, strains, and etc. So with the combination of the process deviation or process data, then you are able to predict the probability of failures. So the role of the integrity, or what we call the knowledge engineer here, is to interrupt or to do the manual confirmation when you see there is a substantial evidence of the defects and the deviations. So you also see in the center here is a knowledge-based or intelligent system. So this module actually acts like I would say, the CPU in a computer in this system. So it collects the real-time abnormal defects and deviation data, and then makes computations with the help of the statistical classifications techniques. You can use AAN or you can use BN, whatever. And then it also involves the feedback inputs from the knowledge engineers or the integrity engineers, and also issue the warnings to the integrity engineers when he or she need to intervene the process. So eventually that the outcome produced by the system will be used for the decision making related to the optimization of the maintenance or inspection intervals and some other things related to the maintenance life of the asset. So this will give you a very brief conceptual picture of how we can estimate the probability of failures based on the condition monitoring data. So basically, we monitor these two groups of the data parameters. So this is related to the asset integrity, to the defects, and this is related to the process deviations or to the process variables. So when we predict the probability of failure, we're looking into this joint probability of failure of these two different group of parameters. So so following these steps, so you will be able to optimize the inspection interval, and also related to do something to enhance or to extend the life cycle or of the asset. So that's some of the conceptual models that we developed before related to the asset integrity management based on the condition monitoring data. So we all know that these days we talk a lot about the digital twin. So I would say that with the emergence of the Industry 4.0, so the process industry is also now considering a wide range of digital technology that we can use to enhance the productivity, the efficiency, and also the safety of the operations. And that also aims to minimize the capital and operating costs. and also minimize, of course, the HSE risks in a chemical plant life cycle. So this is a typical 5 components model of a digital twin. So you will see that there is a physical space, and this physical space contains the physical assets, the sensors and the actuators, and the virtual space is the digital mirror for the high fidelity simulations of the physical counterparts. So the service system is containing other software tools that we can use for visualizing of the service, or for the product quality service, or for the diagnostic service, or for the model collaboration service, and this kind of computational service. So you will also have a digital twin data fusion model in this 5-component model. So this data fusion model is actually a bridge between the physical space and also the virtual space, and also the service systems. So this model collects the data from multiple sensors, and then the simulations, and also the service systems. So then eventually the collected data are fused and then analyzed by the digital twin data fusion models in order to generate the driving commands for the other 3 modules. So the connections are just the wireless or wired communications between these modules. So this is a basic a framework of a digital twin model that probably be used in the asset integrity management. So some of the enabling technology are listed here. So we see that the majority of these enabling technology are for first the data acquisition and the communication, and then for the data analysis, and then eventually for the visualization of the outcome of the data analysis. So, so some of the recent study shows that the most popular application area of the digital twin is actually the asset monitoring and the maintenance. So, people are actually very promising about the application of the digital twin in the asset integrity management in the process industry. So there were actually opportunities and also challenges. So the digital twin can acquire the data for the asset performance management in real time. And these assessment will include, of course, the structural integrity level of the assets, and also the potential failure models and rates, for failure modes and rates, and also probably the requirement for the repairs and replacement. So, and the digital twin can also provide a single interface for, I would say, a visualization of the risks, and also the key performance indicators of the assets. So operators can now use these insights and indicators to optimize the assets, and can also optimize the plans for the intervention for the repairs and the replacement, and also maybe perform the what-if simulation scenarios to enhance the production while also reducing the downtime. So there is another opportunity that we can use for the asset risk assessment. So we can use the machine learning, deep learning, artificial intelligence algorithms to detect and also to correct asset malfunctions. So then we can also do the fitness for service analysis for each of the physical asset, which is connected to the digital twin. And then we can do continuous monitoring and try to identify the potential failures and avoid the accidents. So another area that is promising for the application could be the collaborative decision making, because we know that the process industry is a very capital intensive industry. So, and it is very important for us to maximize the uptime of our facilities. So when we try to make the right decision properly is also very crucial to this. So, but when an asset encounters a critical situation, so the multiple experts may need to review this situation and also discuss and then collectively develop a scenario to resolve these issues. So as these kind of collaborations among the experts is challenging when they are not located in the same place or near the facility. So the digital twin can actually provide the opportunity of making this happen virtually. So they can still, view the physical components virtually and try to make the decision according to the situation they see. So then, of course, they can also be made for used for the virtual training. So then I will also discuss a little bit about the challenges. So one of the most critical challenges is actually the lack of the standardization. So we understand that the data is definitely the backbone for the digital twin. So, but the data may be unstructured. And also the data integration systems or the platform from different vendors or the plant owners may also follow different standards and methods to represent their data. So the existing data is actually typically not very well linked to a common database, and actually it is often stored in separated locations. So these factors make it very challenging to integrate all the existing and the real-time data into a single data analytic module. So then when the digital twin creates the cyber-physical connected environment to the platform in a real-time manner, so then, of course, they are also vulnerable to the cyber attacks. So we also have to think about how we can develop advanced cyber security protocols that can be implemented to protect both the physical and also the virtual facilities against the cyber attacks. So last is something related to the data ownership and sharing. So the data actually generated within the digital twin can also be used for further development. So that will be including, say, design of new and improved assets, and for also development of the advanced data science algorithms. So then the IP, the intellectual property rights of these data becomes an issue. So we may also have to think about how we can manage these issues. So then something related to the data storage and analytics and business models and people and policies. I will not go too much details in that perspective, so to save time. So, you will see that in last year, so the DMV actually have already proposed a published digital twin model. If I understand it correctly, it's nothing but integration of a digital twin model plus a risk model and also the decision models. So we will say that traditionally then the risk assessment have been conducted manually or and usually offline, and also delivered as a static reports, right? So, and then by using the DMV model, so it presents a concept of which enables to connect the digital twin to the published risk model. So this can let us do risk assessment online to support the risk-informed decision-making in operation. So if you're interested in, there will be a web app. So you can probably try and to see that how it can be used for the pipeline structure reliability assessment. So that's about the model itself. And when we move into the asset integrity management, so one of the key issue is what we call the inspection and maintenance. So the RBI is in the risk-based inspection is actually an element of the technical integrity management, which I would say that is very closely associated with the efforts to sustain the ability of the physical assets to perform the required function either effectively or efficiently without harming the personnel or the environment. So we can also use some of the machine learning approaches in this area. So previously I discussed, we talked about a lot about the big data, but actually when we have abundance of data, there was still some of the missing information or the missing input that we may use for the asset integrity management. For example, the main challenge for the operators to say perform a valid quantitative risk assessment is their limited access to some types of data which prescribed in the standard framework. For example, the API 581 or 580 framework. So some critical metrics in the assessment, for example, the measured thickness or the actual corrosion rates are usually unavailable, and because they are also very costly to obtain. So to assess the component's integrity state in a quantitative way, so in these cases, so we can also adopt the machine learning approaches. And so we have done a very straightforward or a brief application of the machine learning approaches to identify the key material failure modes of the process facilities when we, for example, encounter some of the sample components with the missing input on the design, and also or the other inspection parameters. So the results shows that the approach performance in the risk matrix prediction is again very highly dependent on the model's training data quality, and also what we call the biased variance characteristic of the use models, or the feature that we selected to train the model. So this figure shows you a hierarchical risk value chart for each of the damage mechanism failure modes, which based on which we can also trace back to see which is the most critical failure modes. So it doesn't matter which model that you choose, and doesn't matter how many data do you have. So the model performance, I would say, is very quickly dependent on the training data quality, and also the feature chosen to predict the optimal parameters. So I would say, so the problem that now we have is we should go back to see that how the information theory can provide some of the insights or implications to the development of the machine learning approaches for the asset integrity assessment. So if so let's say that the problem or the question is that when we have the data D, and when we have the knowledge, which is the current model that we have, and we'll try to develop a new model, and actually how something that we need to determine whether this model is a good model or not is whether the model can provide a full spectrum of the information about the real systems or the real physical systems or not, right? In most of the cases, or in the absolute majority of the cases, I think the answer is no. So then what we're trying to do is actually we should reduce the uncertainty of the model, which is in the other way, in the language of the information theory, we should reduce the entropy of this model. So in a nutshell, I would say the probability of, let's say the model is a probability failure model, is definitely knowledge-dependent variable, which is representing our belief in the failures at the present moment. Then addition of the new data can use to update the model and try to reduce the entropy of the model. So we're trying to do some of the exploratory studies in this area to try to link the information theory to the machine learning approach that can be used in the asset integrity management, and also in process safety at large. So with this being said, I just want to summarize and try to give you some of the takeaways from my presentation. So I would say that the risk in the asset integrity management should be modeled in a dynamic manner. So especially when you're dealing with the conditional monitoring data, which is changing with the time. So the integration of the probabilistic risk models with the digital twin may already provide a very promising framework for the asset integrity management in the context of safety 4.0. So the machine learning may enable us to develop models that can analyze larger and more complex data sets, and that it can also deliver faster and more accurate analysis and result. But in order to develop these good models that we can utilize in the risk assessment or the asset integrity, process safety, so we probably have to look back into the information theory. So in the information theory, machine learning, I would say these are just the two sides of the same coin. So with this being said, I would like to thank you for your attention. And if you have any question, I'll be more than happy to entertain. Thank you very much.
Many thanks, Dr. Ming, for your illuminating presentation on these new items for and new opportunities for Safety 4.0. We have to move to next presenter because we are a little late, but I invite all delegates to contact you directly. I'll give your email at the end of the webinar. Sure. Now we can move towards the end of the spotlight of our spotlight talk, and share my. And we are moving on a high note with the presentation by Genserik Reniers. Genserik Reniers is a Master of Science in Chemical Engineering. He is professor at the Safety and Security School Group at the TU Delft in the Netherlands, where he teaches reliability analysis and risk management. He is also professor at the University of Antwerp and the KULeuven in Belgium. He has a wide research interest in the collaboration with surroundings and security topics and socio-economic optimization with the chemical industry. He serves as editor of the Journal of Loss Prevention in the Process Industries, and he is associate editor of the Journal of Safety Science. He authored or co-authored more than 40 books on process safety and related issues. So please, Genserik, the scene is yours.
So thank you, Bruno, for your nice introduction. I was under the impression that we had time until 3:30, so I really will go very fast because I have actually another meeting. I already had another meeting, but I still have another meeting at 10 to 4, so I try to be very brief, very quick. Can you see the PowerPoint now? Yeah?
Yes. Perfect.
Fine.
So I'm going to talk about something completely else, which is, in my opinion, also very important for the future of chemical engineering, or let's say loss prevention of the future in the chemical industry, which is cluster thinking and thinking about industrial parks. As we all know, there are, well, hundreds of industrial parks, chemical industrial parks in Europe, and thousands in the world. Yeah, because companies tend to cluster all the time due to benefits of scale of all kinds. Of course, this has some implications, so I will not explain myself, many books. In the Netherlands, we have an initiative by the government together with industry and academia that started 5 years ago. There were 5 roadmaps that were erected to really talk about the safety of the future, and one of the roadmaps was clusters and what it holds from a safety and security point of view to have a cluster instead of a standalone company. The other ones that you see here are, well, of course, process safety education and knowledge about it, the transparency, importance of transparency for process safety, the importance of thinking about improving legislation on process safety, and what we saw from the previous presentation, sustainable asset management. But in this talk, we're going to talk about thinking and what it means to be clustered for safety from a safety point of view. So we did an exploratory research using a multi-method design, but all qualitative. So we did not do any quantification yet. At present, there is a follow-up research that is going on, that is ongoing, and that is more like a quantification of the parameters. But the research question of this research that I'm now going to talk about is, what are the parameters that influence safety and security in petrochemical clusters? And then you should think about process safety and process security, which are of course of most importance. And to what extent are the parameters present within non-clustered, standalone chemical companies and clustered companies? As I said, it was qualitative research, a literature study, 67 interviews with people from the industry, most people from the industry, but also people from academia, and especially people from, of course, government organizations like inspection services, environmental inspection services, and safety inspection services. All kinds of relevant documents were investigated, not only scientific papers, but also relevant documents within the Netherlands, provided by the experts of all kinds. And a questionnaire was also conducted in inspection services. First of all, we defined a cluster. A cluster was defined by plants in each other's vicinity. So there has to be a geographical proximity. Not necessarily that domino effects, as I will discuss later, should be possible between them. There is a geographical proximity where there is some kind of influence from one company to another company due to the geographical proximity. The mindset of the cluster is to look broader than just the fence, and also to look broader than just the legislation, the European Civil legislation, which calls establishments where domino effects are possible in between a cluster. Now, what are the differences is one of the questions between the clusters and the standalone companies with respect to accident scenarios. Well, if you look at the using the bow tie as a metaphor, and you look at the preventive side, the proactive side, they are the same. I mean, the hazards are, well, flammable substances. Well, we all know that we are dealing with chemicals, but dangerous substances. So the flammability, the explosivity, and the toxicity are the hazards, both in standalone companies and in clustered companies. And also the central events would be then fire to some extent, explosion, and toxic clouds. Of course, in the consequences, there will be differences between standalone companies and cluster companies. In a standalone company, you have the regular damage within the company, the damage outside of the company due to an accident, for example, to residential areas and buildings, and escalation effects. And I will explain in a minute what is the difference between an escalation effect and a domino effect. And in a cluster, that you have the same, but you also have the possibility of damage within the cluster to adjacent companies, which will lead to different kinds of losses, as well as domino effects, as well as chain effects. So the difference between escalation effects and domino effects, domino effect is actually between two companies, company X and company Y, from one installation to another installation between two companies, because we use the definition from the Seveso legislation for when we talk about domino effects. And the escalation effect is actually within an installation, within a company. So it means that you can have a domino effect which is inside the company, which is actually sometimes in scientific literature, it's called internal domino effect. We call it an escalation effect to make the distinction very clear. So the domino effect is an external domino effect. On the other hand, besides the domino effects between the companies and the escalation effects, so the knock-on effects within companies, you also have chain effects, and chain effects are accidents that can happen due to the fact that companies in a cluster, a geographically situated cluster within where companies are situated in each other's vicinity, that they make use of the same utilities, or the same streams of products. So there can be a problem with utility from one company to another, or to, for example, the raw materials from one company to another. This can cause also an accident, can actually cause also a major accident. So that we call a chain effect. Now, so we know that there are domino effects, escalation effects, chain effects. What are now the influencing safety parameters in clusters? If we talk about, well, prevention and mitigation. Well, this is really in a nutshell, because I already made a very brief summary of the results, but in a nutshell, first of all, there is of course the parameter of cooperation and knowledge sharing. It will lead to reducing costs if you share knowledge and cooperation, and to a higher quality and professionalism of safety measures, in principle, if you can take from each other the best of good practices. But there are lots of challenges if we think about the results from the interviews that we held. A lot of challenges, for example, some challenges that the cluster is usually not originating from one company who was divided into several companies over the years, but just that a company was there and another company came next to it, etc., etc. So not originating from one company. So it can be a challenge because all these companies have their own mother company, etc., and their own way of doing things with respect to safety, which is of course very good, but it may be a problem if you want to really cooperate and coordinate and cooperate on safety. There is not so much integration sometimes, and interdependencies are not, if they are not there in the cluster, it's more difficult to cooperate and to share knowledge. And there are other challenges beside these challenges that I just mentioned here. Exchanging information on accident scenarios would also be, and it's actually asked or demanded in Europe by the Seveso legislation for domino effects at least. But this is really an influencing parameter, an influencing safety parameter for clusters. So the Seveso legislation asks that there is an exchange of information regarding accident scenarios if you are an establishment with the domino designation. You're obliged to do that. You can also do that for other accident scenarios, not just domino accident scenarios, of course. If you have multiple companies that together form one establishment, which is sometimes the case, then you have no obligation. Although you are, well, multiple companies with multiple management, top management, and multiple policies with respect to everything. I mean, you're really different companies, but you are one establishment. So no obligation, which is not really logical. Effects are possible without domino designation between the companies and between non-Seveso companies. If you are a risk-relevant company, for example, just not a Seveso company, but still having lots of dangerous goods, but just below the threshold, you can be really subject to another company, or you can be of danger to another company. Effects are possible in between. Another thing is, of course, what is the quality of the information exchange? There is information exchange necessary between companies who are domino designated, but the quality is unclear. Sometimes it's just exchanging paper instead of really exchanging high quality information. Well, most of the time this is the case. So cooperation is more, of course, than just exchanging information. It's also about cooperation. Standardization and uniformity is also influencing safety parameter. You can think about talking with each other about how to communicate about safety, what are the safety rules, what are risk analysis, how can we share information, and in a way that we both understand what we are saying and that we have the same interpretation, etc. Due to standardization and uniformity, in principle, the complexity would decrease, the ambiguities and the different interpretations would decrease, the indifferences would decrease, and you would come to some kind of quality level, which is, well, a level playing field, or let's say similar with each other. In practice, there is some uniformity, but much more uniformity is possible. If there is uniformity in safety, mostly it is about occupational safety. It's not about process safety. In process safety, there is not so much uniformity. It also depends on demarcated areas. Yeah, within the areas, okay, it's okay. There is some uniformity, but outside of the areas, and you have several demarcated areas in one cluster, for example, it's less. And it's more operational than strategic or tactical. Well, it's mostly operational. On the other hand, of course, it's mostly also reactive and not preventive. Because if we talk about mitigation versus prevention, the cluster cooperation and initiatives currently, they mostly or they solely focus on mitigation, on the reactive part. You have a joint fire brigade, for instance, in some clusters, or joint crisis management exercises, or emergency plans that's present, but it's of course reactive and operational. And to a lesser extent or non-existing, prevention. Joint prevention, so exchanging information with each other in a uniform or standardized way, investigating accidents in a uniform way, jointly carrying out risk assessments or threat assessments, for example. These are all possible ways to improve cooperation with respect to prevention in a chemical cluster. Laws and regulations, there is some kind of a paradox, because the government in the Netherlands and in most countries, they actually give incentives to companies to cluster. They like companies to be situated in chemical industrial parks and not in as a standalone company far away between the residential areas. So there is some kind of a push to cluster on the one hand, but on the other hand, once the companies are clustered, from an inspection point of view, the companies are still treated as standalone companies. I mean, there is no inspection at all, for example, looking at how companies cooperate, what is the quality of exchange of information, what is the quality of cluster safety, with respect to chain effects, escalation effects, and domino effects with each other, and other safety issues that are specific for chemical industrial parks. So some recommendations for safety in chemical clusters. Well, first of all, try to stimulate and improve information exchange accident scenarios between adjacent companies, with and without domino designations, these companies. More attention for possible domino effects with companies falling just below the Seveso threshold, or being considered not so dangerous, but still can be part of really a major accident. Try to be more proactive and strategic in the cooperation within the chemical industrial parks. A cluster policy should include more than just spatial planning and external safety. Cooperation should be stimulated and knowledge should be shared within clusters and between clusters. Also between non-clustered companies, and uniformity initiatives should be given incentives. So a little word about security. Of course, security was also part of the study. We also draw a lot of conclusions about security, which I also summarize here in a little nutshell. There is a difference between safety and security, because, of course, the worst credible central events are the same for both safety and security, more or less, in the sense that, for example, in physical security, it's possible and even credible that multiple central events take place simultaneously. So the end consequences could be much worse. Also, you have to take into account that the existing control measures now at place for safety reasons will not work in case of security, if they are intentionally disabled, for example. It's a little bit the same as with the presentation on Natech. You have a lot of barriers, but if the barriers do not work, take this into account in your threat assessments and your possible consequences when you deal with security in chemical industrial parks, for instance. The influencing parameters are similar: collaboration and knowledge sharing, standardization and uniformity, They're all very important for security as well as for safety. And they will improve the physical security level. But one thing should be taken into consideration: the degree of transparency is different, of course. In safety terms, you try to be as transparent as possible. In security, this is not possible. So in security, you should form trusted communities, and especially in clusters or industrial parks where the geographical area is determinant, this is of course possible. So you need to be open in seclusion, let's say, in a trusted community, just like in other industrial sectors such as aviation. Within demarcated chemical areas, security is often dealt with in service level agreements, and people already talk with each other, and in these trusted communities they already exist a little bit. But for example, threat assessments, they are not jointly carried out, or at least to a much lesser extent in chemical industrial areas. Current measures mainly focus on aspects such as camera surveillance, fencing, access control. Conclusions with respect to physical security. Well, due to the scale, there is some positive side and some negative or disadvantage that I will discuss. The benefits or the advantages are that due to the scale, the clusters are easier to protect. So taking joint security measures lead to a higher quality and professionalization, and the complexity makes it difficult to really carry out a successful terrorist attack, for example, within chemical clusters, because you have to do a lot of homework and you have to have a lot of knowledge if you want to do this. But the disadvantages of clustering is that there are larger volumes of dangerous chemicals within clusters as opposed to standalone companies, which are possibly the possibility is there that you can use them for bigger impact, for more consequences. And due to the scale of a cluster, it's also a downside because it is more difficult to secure. If you have fences, etc., you're difficult to secure, and you should rely on your neighbors or to the companies who are really also applying physical security measures in your vicinity. The anonymity in a cluster is bigger, so certain actions are less likely to be classified as suspicious also, instead of in a standalone company. So I think these are the main, really in a nutshell, the main results and conclusions from the research that we did in the Netherlands. And as I said, now we are doing a follow-up research, trying to quantify the parameters within the clusters. Bruno, I hope this was...
Yes.
If you have any questions, I would be happy to answer, or they can also send me emails.
Thank you very much, Genserik, for presenting us clustering safety and security approach. Certainly burning issues for the whole Europe for the future. And I invite presenters, and also many thanks for keeping a restricted time and going rather fast.
What I forgot to mention is that, of course, for resilience, because Hans started with resilience, chemical cluster or looking at safety, process security from a cluster point of view, I think will be very important in the future.
So we close the loop in the right way. Thank you once again. I invite all delegates who want to explore further this item to contact you directly. I'll leave the email, so I know you are busy. So I share now my screen. I thank you again. We are going at the end of our spotlight talk. I'm very happy to see that we have a large attendance until the end of the webinar. And I wish to thank the keynote speakers for sure, all providing us food for thought, and all the virtual delegates, especially those stimulating interesting discussion. I'd like to close the EFCE Spotlight Talk, inviting you to Praga Symposium, which is chaired by myself as a chairman of the Working Party on Loss Prevention, and Alex Bernatic, who is the chair of the local organizing committee. Here you can see the call for abstract, which is going to be open. The deadline is 15 May 2021. And there is also the call for the 5th EFCE Excellence Award in Process Safety. The call for nomination will be available on the website of the EFCE. And so please, a young researcher, those of you who are the rising stars in the process safety community, please keep an eye on EFCE website. We shall welcome a new generation of process safety professionals, we hope, with a broad interest in both technical and human organizational aspects of loss prevention and safety 4.0 for the benefits of the European process community. So I leave here the presenter emails. I wish you success for the future webinar, which I invite you to attend in the next days, still promoted by the European Federation of Chemical Engineers. Goodbye to all, and thank you once again for listening to me.